The concept of R square in linear regression is the same as that of the R square in ANOVA. Suppose the average mean systolic blood pressure of all the participants in our study is calculated to be 130 millimeters of mercury. Now focus on this one individual. He had a systolic blood pressure much higher than the mean systolic blood pressure of all the individuals. If there is no association between BMI and systolic blood pressure, we would see that all the individuals will have their systolic blood pressure around the mean systolic blood pressure line, right? But we see that some of them are slightly lower, specifically for the ones who have lower BMI, and some of them have higher, which roughly correlates with the higher BMI. Now again, please focus on this particular individual. He had a systolic blood pressure which is almost 13 millimeters of mercury higher than the average. Now this variability or this difference from the mean systolic blood pressure is partially explained by the higher BMI, right? Because he had a higher BMI, so this he is supposed to be having systolic blood pressure somewhere here, as per our regression line. But there is another part of the variability which we call the unexplained variability, which is caused by the natural variance among the participants. So in a nutshell, there is a total variability per person or per participant of per participant. For this individual, it was 30 millimeters of mercury, partially explained by higher BMI, which is 15 millimeters of mercury, and partially unexplained, which is 15 millimeters of mercury. So in short, total variation is the sum of explained and unexplained variation. And explained variation in regression line is the portion which is predicted by the model. In this case, it was BMI. And unexplained or the residual variation is the random error, which is not captured by the predictor. And once you have the total variation, which the sum of explained and unexplained variation, you can then calculate the R square as follows. The R squared statistics measures the proportion of variability in the outcome explained by the predictor. So R square is equal to explained variation divided by total variation. And like ANOVA, we call the explained variation as the model sum of squares, and total variation is calculated by total sum of squares. Suppose we get an R square of 0.8. This would mean that 80% of the variation in systolic blood pressure is explained by BMI, although this much high R square is very rare in health sector. R square thus provides a measure of how well the model fits the observed data. So in other words, R square measures the model fit, and it is the proportion of variation in the outcome which is explained by predictor. It ranges from a 0 to 1 or 0 to 100%, where 0 means that model explains none of the variability, and 1 or 100% means that model explains all the variability perfectly. Higher R square means better fit, but of course the context matters. A high R square greater than or equal to 80% or 0.8 indicates strong explanatory power of our model, but it is pretty rare in health data. An R square between 0.3 or 0.5 would fall in the category of moderate R square. It indicates a kind of a small variation captured by the predictors. And an R square which is less than 0.2 or 20% explains the model very little, but it may still be useful depending on the context. Even R square of 0.1 can be meaningful in the health sector if the predictor is clinically important. R square has several limitations. One is that it will keep on increasing as we keep on adding more and more predictors, even if they are irrelevant. In this case, we use adjusted R square to correct for increased number of predictors, which is also called the penalized version of R square. As is the case in almost all the concepts in statistics, R square does not imply causation. It only indicates an association. A good R square depends on the context. For example, in physical sciences, often more than 90% or 0.9 R square is required. But in social and health sciences, even 0.1 to 0.3 might be valuable depending on the context